Our project is about the deployment of indoor point clouds for firefighting strategy. This geometric synthesis project is executed by Charalampos Babis Gatsidiakos, Jos Veenstra, Ruben Hurkmans, Max van Schendel and Camille Morligem. Our clients are CGI and the Safety Region of Rotterdam, represented by Rob Wachaar and Huip Fransen. Our supervisors from the TU Delft are Edward Verbree and Robert Wouten. Imagine a team of firefighters being called to fight a fire inside of a building. This is called the alert phase of an emergency response. They hurry over to their fire truck and go to the location of the incident within the en route phase. Once arrived, they equip their protective suits and start exploring the emergency site to gather as much information as possible. This is called the exploration phase. The information gathered within this phase includes the building's characteristics, the nature of the incident, and the location of the fire. This information is essential to determine which strategy they use to fight the fire and to rescue whoever is inside. The person responsible for defining these strategies is the incident commander. The incident commander supervises and interacts with the team remotely. Despite the high stakes and stressful conditions of a fire, the commander has to be able to make important decisions in the nick of time. However, the commander does not have visual feedback on what is going on inside a building, and a wrong decision might lead to decreased effectiveness or even casualties. Besides the overarching strategy, firefighters also need to take decisions within a limited time frame. Situations that the strategy has not taken into account are bound to happen, and when they do, how the firefighter responds may mean the difference between life or death. When making split-second decisions, it's not just the amount of information that matters, but also how quickly and easily you can access it. To provide the fire response team with the information they need, when they need it, we created Incident Mapper. Incident Mapper is a real-time collaborative information system which can collect, process, and distribute information about the scene of an incident and the people involved in the emergency response. The system consists of two modules, the Explorer and the Navigator. The first module, the Explorer, is used by firefighters in the field. It tracks the user's position inside of the building while simultaneously creating a 3D map of their environment. It also allows its users to manually add information to the environment and to view it using a head-mounted augmented reality display. The other module, the Navigator, is used by the commander of the response team. Its main purpose is to dynamically combine information from multiple explorers into a single model in real time. The Navigator also allows its user to view the model in different ways, to interact with it, and to distribute information among the explorers. By supporting the feedback loop of gathering information, making decisions and taking actions, Incident Mapper could make fire response teams more effective and reduce the risk of field operations. The first component of the Incident Mapper to be discussed is the Explorer. The Explorer makes use of a head-mounted device called the Microsoft Hololens, which continuously captures its environment and records its positions relative to it. This data is recorded relative to the HoloLens starting position. This is problematic because we want to combine data from multiple explorers that each have a different starting point. To solve this, we used a method called spatial anchors. A spatial anchor essentially serves as a common reference point which can be recognized by multiple HoloLenses. It works similarly to how humans describe the position of an object or of themselves relative to a landmark. As we could indicate the position of a bus stop by saying the bus stop is 100 meters to the left of the statue, multiple explorers can describe their position and environment relative to a spatial anchor. By projecting light onto an internal display in front of the user's eyes, the HoloLens can also overlay virtual objects called holograms onto the real world. This means we can show information to the user in a way that does not interfere with their work. By performing a pinching gesture, the user can summon a menu in which spatial markers can be chosen and placed in the environment as holograms. This menu can also be used to place spatial anchors and to toggle the lifeline. When the lifeline is toggled, the line connecting the user's position over time is displayed. If the user loses their way during a deployment, they can simply follow the lifeline back to where they came from. The display also contains a minimap in which the position and orientation of the firefighter is shown, as well as the position of objects in the scene, which can be used to get a quick overview of the scene itself. The Navigator application acts and serves as a centralized hub or cloud. It can send, receive, store, classify and visualize spatial data. It also offers a UI to control how it is used, to look at the data and to interact with it if it is being captured in real time. The Navigator is meant to be used by a commander or other supervisor and shows an overview of all data currently being captured by all personnel in the field. It also shows the position of these explorers, and it offers ways to interact with them using position-based commands. Explorers capture their surroundings directly as meshes. The Navigator platform offers different ways to view this continuous stream of meshes. The model can be visualized as a point cloud by only showing the vertices. This is useful for overlaying multiple different datasets. Another visualization is a transparent wireframe mesh. This makes the surfaces more readable without obstructing other meshes. Thirdly, the Navigator offers fading visuals by giving meshes an expiration date. A mesh previously sent might not be accurate anymore if, for instance, a car has moved or if a wall has collapsed. Lastly, the Navigator can show how the meshes are classified as a floor, wall, ceiling or a piece of furniture. The Navigator is able to track and receive data from multiple explorers at once. This allows the user to get an accurate overview of the position of personnel. By distributing the position data back to explorers, they can track other explorers in augmented reality, even allowing them to see where other people are through the walls. The main reason for which real-time capturing and visualizing data is needed is to directly make the data usable as a means of communication in the field. A simple way to do this is by creating and sending spatial markers. These can be added into the Navigator environment, which is then automatically synchronized to the explorers. Using the markers, the incident commander can signal the positions of objectives to go to or calamities to stay away from. This project can serve as a baseline for multiple other research topics. A first research topic could use contextual data as a starting point. Integrating the indoor 3D model within the external shell of buildings by using GPS would put the model in a much broader context. The second research topic is sensor fusion. This research topic should not focus only on Hololens or even on mixed reality devices in general, but also research should be done on utilizing any other external type of sensor, such as thermal sensors, smoke detectors, Wi-Fi, or conventional LiDAR sensors, which could massively improve the functionality. Robotic substitutes like drones or terrestrial scanners could replace firefighters in situations where exploration is dangerous. Bringing multiple datasets, like the ones generated by a single HoloLens, within the same coordinate system gives us the ability to overlap the layers. What would be even better is one integral model, instead of several separate layers. The last research topic is immersive user experience. In this project, we have only scratched the surface of the possibilities the broad field of extended reality can have on using and experiencing datasets. For example, the Navigator can also run on a HoloLens for a more immersive experience of the data gathered. Thank you for your attention.
Thanks.
Thank you.
Great. Yes, you're muted, Bastiaan.
Sorry, I was muted, so that explains why I was so late in this meeting. Thank you very much, team. It's very interesting presentation, but we also have some interesting questions. Let's start with a question of your supervisor, Edward Verbrey. First one, if you in your video you don't show semantics like the wall, floor, doors along the geometry, but you did so during your project, what is more important, detailed geometry, meshes, or less points with all deep learned semantics attached to them in real time?
Yeah, that's basically two questions. Abis, why don't you answer the first one? So what did we do with the semantics?
Yeah, first of all, maybe you can stream your screen, and Camille
Yes.
can talk about the classification, and I will talk about the more complex semantics, which is explored in details in the report. We can show it really briefly what we did. Camille, you can start with the classification if you want. And you are muted. I don't know if you see it.
Sorry. So we implemented the classification algorithm. So basically, the Hololens, they gather meshes, and we basically we compute some properties of those meshes, like the minimum height, the maximum height, or the average area. And based on that, we compare those with thresholds, and we can determine if the surface of the meshes is either the floor or a wall surfaces or the ground. And I cannot see the screen because my computer is loading, but it's possible also to show only some parts of the meshes. So you could choose to show only the walls in the Navigator, or to show only the ground. And that way it can help the firefighters to have a better understanding of the indoor space.
Yes, and to answer the second question.
To add also, sorry, something to the semantics part, I can say about another functionality that is linked to semantics, about the more complex semantics, the door detection. As you can see here in the example, I won't go much in details how we detect the door. Basically, it's intersection between wall planes and line segments that created from the trail of the user with the HoloLenses. As you can see in that room, the door is detected. We implement that algorithm to add more complex semantics. It's important to mention that in order a door to be detected, there are two requirements. So yeah, firstly, the walls next to the door should be scanned properly, and secondly, the user have to pass through the door and not just to scan the door. But yeah, we find that this can be useful to firefighters, this knowledge before entering a building. So that's about semantics.
And the second part of that question was about what's better, basically a lot of data points, or maybe just like a point cloud of data, or do you want to dense that down to just some key points? And as most of these questions, the quick answer is it depends. Because, for example, you also run the risks, always run the risk with classification algorithms that it's not properly classified. Plus, it costs computation time. So it's a balancing act between giving clearer information, because this is clearly a lot harder to read in one glance than maybe just let's say a classified point cloud where we turn the furniture off. But yeah, if you want that more complicated or more high-level abstraction like that, you run the risk of not classifying things properly, so weird glitches, and yeah, a larger computation time, so a larger time between the response team doing something and the commander reacting to it.
Okay, thank you very much. Edward had another question, and that is on this Boston Dynamics spot dog. Basically, the question is, can it replace a real person, the real firefighter?
Can I answer this question?
Of course you can.
Well, the situations where we imagine such a robot could be used is as the absolute first responder, the first person to enter a building. And although they might not completely replace humans, they don't have the ability to improvise like humans do, they could be a good replacement to get a first overview situation, is the most dangerous part of the deployment, the first person to enter, and then transfer this information to other firefighters. So not a replacement, but an improvement in some situations.
Okay. Very glad to hear that we're still useful as human beings. Then Lawrence has a question. Do you know how these spatial anchors are found and matched?
Yes, so they are not found. We create them manually. You can indicate the position. And basically what a spatial anchor contains is a point cloud, which is scanned by the Hololens, and a collection of other sensors, such as the camera feed of the Hololens, and it also contains the Wi-Fi fingerprint of the current location of the Hololens. And all of this data together can be used to match the current position of a HoloLens to the description of the spatial anchor. This is all proprietary, but we can, in our report, we discuss several methods which they can use to, for example, match point clouds independent of rotation and translation.
I think that answers the question. And a question by Ravi Peters, a more practical one. Well, this HoloLens is quite critical, but does it still work when there is a lot of smoke in the building?
I can answer the question. So it doesn't work with dense smoke, but yeah, with maybe sparse smoke it works, but not with dense.
Although it should be mentioned that this is a few years old at this point, and future iterations of the HoloLens could improve this.
This is still a big practical obstacle to use for firefighters, I would say.
Yes, certainly. And, this project is just a prototype, but it still depends on some technological improvements before it can actually be used in the field.
Clear. Okay, then Maarten de Jong asks, what kind of GPU is required to visualize this data in real time?
Just a regular one. It runs a laptop on Jos's computer, so it's no.
Can I?
Sorry.
Yeah.
Please answer one at a time. Yeah.
Yeah. Sorry. But you don't need an advanced system. This can be built and run on a tablet. So you don't need. Although we built this thing inside of the Unity platform, which is primarily a game engine, it's not heavy at all. So I hope that answers it.
Okay. Yeah, that's also the other question: how far is data simplified to keep it fast enough? There's no need to simplify it. Huh? Okay, then Peter van Ozem asked, what was all data that you showed in your video collected by yourself?
Yes.
In the video, yes, but the streaming that we did now, it was a CGI Arrow, so it was a message that was provided to us and not data that we collected. But we performed an actually testing, like not all of us could attend due to the current situation. We are in different countries, some of us, but the guys went to the library, so yeah, the data are from there.
Okay, very good. Then we have someone in the skies, RCBNL. What is the range of the Explorers starting from a mutual cloud anchor?
Well, we haven't been able to quantify this exactly, but we were able to at least move around the entire TU Delft library without losing tracking. Although, and Lawrence asked another question about this, the accuracy does remove the further, we only use one spatial anchor, and the accuracy does reduce the further you move away from one.
So a proper future implementation would although we only need one, it's like the usual. What usually happens when you try to merge 2 point clouds together, for example, you want an overshoot of matching data, so you can do some least square adjustments. So yeah, that would be the next step. Yeah.
Okay, then the same RCBNL asks, can cloud anchors be linked to GPS points in real time so that indoor positional data can be streamed to the currently used applications?
Yes, they most certainly can.
Can you explain a little bit further?
The HoloLens doesn't have a GPS sensor, but the Azure Spatial Anchor service that we use also allows GPS to be added to the blob of data that the Spatial Anchor consists of.
Okay. Then Dongyang Peng asked the question, if someone is running, like firefighter is running in the building, is then the system still fast enough to visualize the data of the surroundings?
Yeah, we did a lot of tests about like the reliability on the system under stress. We didn't want to use a like €3,000 tool provided by us by CGI. We didn't want to do too crazy things with it, so we kept it. We didn't use it in smoke to test the smoke range for ourselves, for example. But we did try to move as fast as possible with the system. I've got some data sets I could show them, but the range, as you might see, is very limited. It's about the cone you can see right here. But you can move quite fast if it has enough pre-acquired tracking points. If you move really fast into an unknown direction, without any prior exploration, it will lose tracking.
Although it can regain tracking.
Yep.
Okay, there's some care, some work to do there. Then Geomaticsday, whoever that is, asks, what is the risk of a firefighter truly trusting these kind of applications? Which parts can safely be used, are accurate enough, and which ones should be used with some special care? Can the firefighter trust the system?
These sorts of questions are hard to answer in a yes or no way. But what we can say is that we put a lot of extra efforts on the reliability of the system. And for example, when you try to communicate, so the explorers map their environments, they send their meshes through the Azure Cloud system back to the Navigator. And we made several fail-safes in that whole system that if a small piece of the puzzle was not loaded properly, it could be added quite easily. A sort of chunk loading system, as it were. So I think the reliability aspect is something that can be best addressed by just the coders themselves. So the features must be implemented in a way that that there are several like fail-safes to go back on. But in general, the meshes scanned by the HoloLens are already very much a pre-filtered, and from what we've seen, because it's a proprietary closed system, from what we've seen, they're insanely reliable, albeit very limited. So I would trust those things. I would really trust the just the HoloLens by itself. In a merger, we might, for this to be actually used in a real life situation, it would be really great in a future iteration of the same exercise that there would be some sort of check happening from multiple sources. Is this data the same as what 3 HoloLenses are seeing right now? So to get some confirmation in the system, that would be really nice.
So that's on the input side, and that you also look at the consequences for the let's say the job description of a firefighter. Does the use of this application require intense training, or can you use it right from the shelf?
Max, maybe you want to get into that?
We try to design it to be as non-intrusive as possible, so to be able to be used with hand gestures and stuff like the mini-map. We try to make it as simple and because firefighters don't have time to look at a lot of things in the field, they want to be able to see stuff right away. This is really something we set as a goal from the start to assist the firefighters and not impede them.
The non-GIS experts should be able to use the system right away.
It takes a bit of getting used to the Hololens and the hand gestures, but it should be usable by mostly anyone.
Very good. Then a suggestion by Robert Fouten. Would it be useful to give different floors different colors to be the of assistant of the firefighter?
Yes, and that can be done. By the classification algorithm, multiple floors are detected, and things like ceilings and floors are classified in that way. So yes, that could be the very next step. There are also shaders for point clouds to basically do the same thing. This would even we don't even have to do a classification for that. The points can just be shaded like that, so that would even be more reliable. So there are definitely options.
That's an advice for our architects for the inside interior ones, focusing on designing nice colors in buildings. Okay, then a question by Peter van Oostum. Is the HoloLens 100% based on imagery, or are other sensor types used, like sound, radar, passing through the smoke?
I'll answer that. It is based on a time of flight depth sensor and 2 RGB cameras, and it has a Wi-Fi sensor. But no, it does not use radar, but or other sensors. But in the future, it could be. We didn't imagine this project to run purely on a HoloLens. It could be integrated with more sensors. It doesn't have to rely all on the HoloLens.
Okay.
That's
very good. Then a final question that I have, and then we move on to the next part in the program. So in your report and also in your presentation, you highlight that the network has to be trained, and the training machine is often, let's say, unique. So there's a big difference between training the network for a train station and one for the hospital, and maybe also the hospitals differ a lot in between. Does this imply that the further implementation is still a long way to go?
I think you're confusing our project with the point cloud project.
Oh, is it?
Implementing the deep learning algorithm. This does not need prior training.
This is the wrong. Okay, I'm sorry for this.
But but it's a nice segue into. I think it's really interesting to look into merging these two projects, especially so the project done for the NS. Because if they manage to train a point cloud on just really general buildings, if they get a fairly accurate, fairly reliable classifier in there, and if it runs on one of these chunks of a mesh in near real time, it could be implemented, and then you would get a much more general classification algorithm based on deep learning inside of this tool. So it could, the interaction is possible. I just wanted to add that in there.
Super, yeah. Well, all the projects are connected in the end, I guess. Okay, thank you very much. Big applause for you as well.
Thank you.
Of course, the rest will join you. Then we will continue with a presentation by Fugro, creating a safe and livable world through smart monitoring of urban infrastructure. Mels, you can press the button.